The homework for this chapter, chapter 5, has already been posted on the Grayscope. So you can go to Grayscope and download the template, and then that you can see the homework. So the homework for chapter 5 should be much simpler in compared to the previous homeworks. And the number of questions are also smaller, and you sh and I also gave you quite a bit of hint if you don't know how to do the problems. Uh, for one of the problems, there is an optional question that um, it asks you to use the Biot-Savart law to calculate the magnetic field, and you can choose one of the questions. Um, I'm not remembering. I think it's about question 3 or 4. So there is a question that has a plot of figure A and figure B. You only need to calculate the magnetic field for one of the figures. So if you still remember about the homework coding, the due date is on November the 25th. So if you have any problems with how to plot, you can also ask me or the TA. So in Python there is a built-in plotting function. So but if you write in C and other languages that run in terminal, you might not be able to plot in these languages. So you could use something called a GNU plot or something similar to, or you can even use Python to import your data and plot in Python. So in the last lecture, we discussed the Lorentz force, and the magnetic force is simply QV cross B, and here this one is simply saying for a collection of this charge, the magnetic field is simply the integral over all these charges, and then we generalize that to a linear charge. So for a linear charge, for a line current, so we generalize that to a line current, and for a line current, the magnetic field is simply the integral of I cross B, and in the very last, in the end of the last lecture, we also generalize the line current to the surface current here and the volume current. So correspondingly, we need to change this line charge to surface charge to volume charge, and in the end, we get that the magnetic force felt by a surface current is simply the integral of K cross B, and integrating over all the surface, and all this J cross B integrating over the volume. Now, if you still remember about the last example that we discussed, to convert between the total current and the volume current, we simply need to integrate the volume current across this interested surface. And now we can rewrite this integral by using the divergence theorem. So here we can consider a volume of wire with volume charge J, and now if we impose this divergence theorem on the two ends of this wire, we can actually see that this J cross these two areas, one entering the volume, another is leaving the volume, is equal to del cross J. and convert using the divergence theorem, we can convert this surface integral to a volume integral. And now because this should be both flowing into this volume instead of one in and out, one out. So the n direction of this two surfaces should be both pointing out. And then if we define a Gaussian surface that enclose this segment of wire, and then we can relate this surface integral to this volume integral with the divergence operator. And now because the charge is a conserved quantity, which means that the charge that flows out of this surface must be compensated by the total charge leaving this volume. So here this volume integral should be related to this derivative of this volume charge integral. And because here this is flowing out, so this equals to the negative of the change of the total charge, because flowing out equals decreasing of this total charge. So here this is simply the charge conservation law. And now we can combine these two equations. And also because this applies to any volumes, so we can simply drop this volume integral here. And in the end, we actually arrive at this continuity equation. Del dot J equals to minus partial rho partial T. So this means that the change of the charge is related to this divergence of this current. So you can imagine that in the case where the charge is not changing, then the divergence of this currents must be 0. And that is one of the requirements of this electromagnetic static case. So in the last lecture, we also discussed that the discuss about the relationship between the point charge, point current, line current, surface current, and volume current. And so this is exactly like what you see in this electrostatic problem, where this point charge can be related to the line, surface, or volume charge. It's exactly the same thing here, that you can simply rewrite this summation of QB into the integration of a line charge, a line current, or a surface current, or a volume current. Now, if we compare this, so if you compare the electro and the magnetic static case, so both cases, for the electrostatic case, we require the stationary charge. This means that the field, it produces a constant electric field. And in the magnetostatic case, we require the steady current, and it produces a constant magnetic field. And if we want to combine them together, then in equation, they actually means that the change of rho and the change of J is equal to 0. So in particular, for the continuity equation in this static problem, simply reduce to del dot J equals 0. So if you look at this equation on the very top, because partial rho partial J in the static problem is 0, So naturally, the divergence of the J must equal to 0. Okay. Next, what we are going to talk about is the Biot-Savart law. So what we just finished is the Coulomb force law, which helps you to calculate the force in a current felt in a magnetic field. Here, this Biot-Savart law is helping you to calculate the magnetic field generated by this by a certain current. So combine these two, you can get the total magnetostatic case. So here the definition of this Biot-Savart law, I think if you still remember, you have already seen that in the physics 2041. So here I just write down the equation here. The magnetic field is can be written down also the cross product, where the first one is the current along this wire, and the second one is the separation vector. So here the separation vector means suppose that we have a source current and at here, and then we are observing this so the observation point is at R. So here this R minus R prime is the definition of this separation vector. And here this is simply the line element of a line current, sorry. And here this is the separation vector square. And similar to this electrostatic case, there is the constant over here, and this constant mu naught is called the permeability of the free space. It's a constant. It's approximately 4 pi. So the very definition of this, the precise number of this one depends on the unit. So in the current SI unit is 4 pi times 1.00000, many zeros, and followed by a small correction. So this mu naught epsilon naught is also related to the speed of light. So there is also one question that in the homework that will ask you to compare the magnetic force, the electric force, and the speed of light. And so you have to plug in this number here, and another permeability of this epsilon naught, and these two combined, you can compare the force of magnetic force and the electric force. Now, in principle, from this Biot-Savart law, we can calculate every magnetic field generated by the currents. So, for example, I'll give an example here. So we can try to, here this example is asking you to calculate the magnetic field produced by a long straight wire. So here is the wire, and then they're asking you what's the magnetic field at an arbitrary point. So whenever we see a problem like this, we first need to identify the direction of this magnetic field. And so here the magnetic field is the, I simply copy the equation on top, and there is a constant. And then this then there is this line element that dl, and cross the separation vector. So here, these two elements defines the direction of the magnetic field. So here the dl is to the right, and this separation vector is pointing upwards like this. So if you cross the two, the magnetic field must be pointing out of this screen. So now let's finish this integral. So here, what we have is this. Inside the integral, we have this dl, and we also have the curly r. So in the so for the dl, we can actually so the cross product of the dl cross the separation vector equals to dl times separation vector amplitude and times the angle between them. That's the sine. So here in this in the figure is sine alpha, and the sine alpha equals to sine pi minus alpha, because adding this minus sign and adding the pi both add the negative sign, and negative sign cancels. So this and the pi minus alpha is the angle over here, and this sine, this angle equal to the cosine of the theta. So we relate this dl to this So because this L is also related to the S by a tangent theta, so we can relate this dl by an S cosine theta squared d theta. So because you can do the derivative of tangent theta, that should be giving you 1 over cosine theta squared. And now this means that we can continue this expression. So here this change to S squared over cosine theta times d theta, and times this separation vector and because here this separation vector is also related to S by separation vector times cosine theta. So we can also change the separation vector to cosine theta. Okay. Sorry, I think I made a mistake here. So okay, this is fine for being here, but here inside the integral is dl cross curly r hat over curly r square. So we simply rewrite this to dl prime cross r divided by this curly r cubed. So now inside the integral, we should be able to write the top as an s over cosine theta squared and d theta s over cosine theta divided by this curly r is s over cosine theta and cubed. So now we can have this right hand side as so there are 2 cosine theta cancels 3 cosine theta, and there is hmm? um, 2s cancels the third, so somehow hmm? Let me see. I might have missed a term somewhere. Um, okay, I think I missed the term on sine alpha. So the sine alpha also provides a cosine theta term that I didn't include in here. So there should be a cosine theta term here. So and this should be an s to the power of -1. Okay, so and there is also this so finally what's the b should be mu naught I over 4 pi, and times the integral from theta 1 to theta 2, and we can put the s in front, and cosine theta d theta, and this integral can be evaluated like this, and so in the limit of an infinite line wire, this theta 1 and the theta 2 goes from um, pi over 2 to minus pi over 2. So on the right hand side, in the parentheses, it should be giving you factor of 2. Now we can from this we can combine what we learned in the previous lecture, and calculate the force between the two infinite long wire. So now for two infinite long wire with current I1 and I2, and if they are separated by distance d, this is very similar to electrostatic problem of two infinite 2-point charge. So in the 2-point charge, we first calculate the electric field by one of the charge, and so here we also do a similar thing, that we first ignore one of the current, say that we ignore the current of I2, and then find out what's the B field, and then the B field should be generated by the I1 current should be mu naught I1 over 2 pi s, and now this B field will of course it's pointing into the screen or out of the screen, and this B field will produce force onto the I2, and this force is this I believe it's I2 and so now if you because this is an infinite line, so we have to because the b is a constant, we can put that in outside of this integral. So it should be a mu naught I1 I2 over 2 pi s. So here this s can be I'll just set this as s. Then is the integral of the dl. Because this is infinite long wire, of course this force is infinite, but per line width, this magnetic force is mu naught times I1 times I2 over 2 pi s. In the homework, you will be asked to calculate, compare the magnetic field between the two lines, and the electric field between this two line charge, two line charge. Yes. So there is a subtle difference between moving line charge and a current. So here a current can have a charge neutral. So you can think of this current as a line charge of plus lambda that's moving in velocity v, and the current should be lambda v, and there is also a minus lambda charge that's moving at v equals 0. So because you can think of this, if you superpose transpose the two of this, then the total charge will be 0. But there can still be a current. So a current can be independent of charge. And so in the homework, what we will see is a moving charge with velocity v. That will also produce a current. But remember that because of the moving charge, there is actually also an additional electric field. So you will be asked to compare the strength of the electric field and the strength of the magnetic field between these two currents. So let's take another example. So what we looked at before is a straight line wire, and now we change that to a circular wire like this. So here, this is the shape of the wire, and the current is also I. And now what we are asked is the electric field at the center line along the z-axis. So this problem is slightly complicated because in the previous problem, the magnetic field is pointing into the screen or out of the screen. But here you can see that the magnetic field. The magnetic field's direction is, strictly speaking, not. It's along. We can try to see. So here, the dl is along this direction, and the separation vector is over here. So if you take the cross product, the direction of this two vectors is already. So you have to take a direction that is perpendicular to the direction of the two, and that direction gives you to somewhere around here. So I'm not sure if you can imagine the direction here. So you can see that as we move this dl from one end to form a circle here, and what's the point? The magnetic field also follows this curve, and the direction is the direction of the magnetic field. If you look at my hand, will circle around, looking like this. So there are components that's along this z direction, and there is also along this radial direction. And however, this radial direction magnetic field actually cancels out because we are looking at a perfectly symmetric case. So what's left over is only the projection along this z-axis. So what we are interested here is only to find out the magnetic field along the z-axis. For all the other axes, the magnetic field should be 0. So we need to calculate B along the z direction, and again we use the we write down this constant here, and what we need to evaluate is this dl cross the separation vector hat over the over the amplitude square. So because we are looking at the z component of this cross product. Um, in the end, what we do is to simply times cosine theta with this amplitude. So it should be here this cosine theta. Here this theta is over here, so the cosine theta simply takes the projection of this magnetic field. And now this dl and the separation vector always perpendicular to each other if we are restricting to this z-axis. So this cross product, the sine theta angle between the two is always pi over 2. So what we have is simply dl over separation vector square and cosine theta. And this separation vector is related to this z by sines. Let me see. So this curly r square is related to the cosine theta square equals r square. So then this integral can be related to this dl prime over r square cosine theta cubed, and dl equals to r times theta direction. So in the end we get let me see. So because this cosine theta and r square does not depend on this integral, so they are all put out of this integral, and so the integral gives 2 pi times r. So what's left over is and here this cosine theta is can be re-expressed as r over square root of z square plus r square. And now if you replace this cosine theta by to here, you get the final result of the B field. So what we just talked about is the Biot-Savart law for the line charge, and to generate to this generalize to a surface and volume charge, it's also similar to what we generalize to the Lorentz force law. So we simply replace this I dl by k dA or j d tau. And so in principle, this Biot-Savart law will be able to calculate any magnetic field for any current, because in this magnetostatic problem, the source terms are all the currents, and employing this Biot-Savart law should, in principle, give you everything. But like this electrostatic case, we calculate the curl and the divergence of the E. So the divergence of the E can actually be related to the Gauss law. And the Gauss law actually help us calculate many electric fields. And likewise, here for the magnetic field, we also have equivalent law called Ampere's law. And to get that, we need to calculate the curl of the B. So we will first, for example, calculate the curl of B for a very special case. So for a case of infinitely long wire, so we just calculate the magnetic field for this case, right? So if you still remember, the expression for this magnetic field is over here, and the phi direction is the direction of the B field. So it's along this phi direction. Now we can calculate to get the curl of B. What we do here is to calculate a line integral along a loop that circles around this wire. So we want to finish this loop here, and now this integral is so for a circle around this wire, this integral is easy to do because it's symmetric, and so this B dot L is simply the constant of this magnetic field amplitude times dl integral, and this is a constant, so it can be pulled out of the integral, and what's left over is the closed loop integral of dl, and so this integral is simply the circumference of this path. So it's 2 pi times the s, where this s is the separation here, or the radius of the wire. So in the end, what we get is the magnetic field along this path is actually equal to the mu naught times this current that's enclosed by this wire. And however, this path is actually a very special one. What we calculate is a circular path that's winding around this wire. This is not necessary because we can actually have an arbitrary path that's winding around this wire. And if you do this integral along an arbitrary path, you see that the dl can be separated to, in principle, the s direction, whereas this s is the radial direction, and the angular direction, and the z direction. However, because you can see that the B field is only along this phi direction, so the B dot dl will throw away these two terms, and only this angular term will be left over. And now what's interesting is that the integral here in the angular direction, if we evaluate the integral here, you replace dl by an s d phi, and then the integral reduced to the term here, but the s cancels each other. So in the end, what we have is simply an integral along the phi direction from 0 to 2 pi. And then this means that actually we don't need circular path to enclose this wire, but an arbitrary path that encloses this wire will give the exact same result. That will always be this mu naught times I. And we can also invoke the superposition principle, and say that we not only we have one wire over here, we can have several wires, and as long as we the path enclose all this B field, the superposition principle simply tells us that on the right hand side it must be the current enclosed. So in the end, what we have for a long wire is that the magnetic field along this path equal to the mu naught times the current enclosed. And let's go a few steps forward. So here this so this current enclosed, we can, if we express that in terms of volume current density J, then we can use Stokes theorem to relate the left-hand side also to a volume current volume integral. And then this should be a surface integral, and the Stokes theorem relates the line integral to a surface integral. So what we have here is surface integral on the left and surface integral on the right. And now this integral is arbitrary because it applies to any arbitrary path. So it also applies to any arbitrary surface, and so because of this surface integral can be dropped. So what we arrive here is the curl of B must be equal to the mu naught times J, where the J is the current density. So here we calculated the divergence, the curl of B in the case of infinitely long wires. So that's still a special condition. And in the next section, we will try to generalize this case and to figure out what will be the expression for an arbitrary general case.